All right, more conversation about things from chapter 2, including things that relate to the line spectra in part, that relate to electronic structure of atoms. This is a complicated but yet historical discussion that helps us to get a perspective on how the scientists of decades gone figured out what was happening in atoms with technology far less sophisticated than we have today. All right, so there was this thing called the photoelectric effect that gave more clues to what was going on with atoms. And when it was discovered that irradiation, shining a bright light on a clean metal surface with light, causes electrons to be ejected from the metal. And the frequency of the light used for the irradiation had to be above a certain threshold value that was unique and different for every metal. In other words, you couldn't get electrons emitted unless it was the right frequency to particularly eject those electrons, to emit the electrons from the surface of the metal. How does that make any sense to you? Well, it's like pounding the surface with enough electrons, but they had to be the right frequency in order for anything to happen, such as analogous to what it would take to break a window. If you threw hundreds of ping pong balls at a window, nothing would happen. But if you put a baseball at the window, threw a baseball at the window, well, shoot, you've hit the right threshold, and of course the window will break. So you have to hit the right frequency of light in order for the ejection of the electrons from the metal. This is called the photoelectric effect, different for every metal. And Einstein, well-known scientist, obviously, had a more detailed explanation of this effect. He assumed that a beam of light was going to behave as if it were actually a stream of particles, and those particles were called photons. You might have heard of them. And their energy is related to their frequency by this number, this value called Planck's constant, and this is Planck's postulate. In other words, energy is equal to Planck's constant, which looks like a italicized h, times nu, the frequency, or h times c over lambda, because nu, if you had not seen this before, or if you forgot, is going to be equal to c divided by lambda. Leads to a really bad physics joke. In other words, what's nu? C over lambda. Okay, so Planck's postulate tells us that the energy is related to the frequency by Planck's constant. And Einstein figured out that if they were behaving like photons, their energy could be related to that frequency. So as the energy went up, the frequency went up, related by Planck's constant. Planck's constant has a value, complex number. You'll use it in a calculation now and then. 6.626 times 10 to the negative 34th joule times second. Don't worry about the units being sensible to you, because constants often have odd units. And furthermore, they were discovering that if the energy had only certain wavelengths for these certain emitted light spectra, that the light had to be quantized. In other words, only certain energies of light were observed, and so the energy of those emitted electrons had to be only certain levels, and those are quantized. In other words, a quantum is the amount of energy for one photon of light. Keep going from there. Well, let's see. So that has to do with particle properties of the energy. In other words, h times nu gives you the energy, because that's how they're related to the frequency of the light emission, the energy of the emission. So another way of representing that notion of the photoelectric effect is by looking at the number of electrons ejected as a function of frequency. And if the frequency is not high enough, you haven't reached the right energy threshold, no electrons are ejected. But when you finally hit the right threshold, you can get ejection of electrons. The plot shows that threshold value, and once you've hit that value, electrons are going to be ejected. And increasing the intensity just increases the number of ejected electrons, but doesn't change the threshold value. So there's a certain value, and how much ejection is related to how much intensity is used. So Niels Bohr, another famous scientist, proposed in early 1900s a model of the atom that as electrons circle the nucleus at specific distances in a series of concentric orbits. That is represented by a diagram we will see in a moment. In that model, the energy of the orbits are quantized. In other words, certain places around the nucleus are allowed for these electrons to occur, but only certain ones. Only certain ones corresponding to specific energies for those electrons. You can't be just everywhere, only certain ones are possible. And it's like saying you can only be on steps in a quantized way. You're either on the bottom step, the first step, the second step. You can't be at step 1.4 or step 2.7. You can only be on specific steps, and energies of electrons are similar to steps in that sense. They're quantized. And so the Bohr model suggests that electrons are restricted to orbits having specific energies, going around in concentric circles or concentric patterns around the nucleus being in the middle, and the electrons are being in the orbits. And if an electron goes from a higher energy to a lower energy orbit, energy is emitted, corresponding to a difference in energy between those orbits. And this has to do with how you can only get certain energy of light emitted from an excited atom, atoms that have been excited by heat or electricity. That's the Bohr model. The electrons are restricted to having orbits only at specific energies going around the nucleus in some fashion. The color emitted by hydrogen atoms in a discharge tube is represented in this picture here. The combination of colors there is a combination of the emission spectra, those various lines in the visible spectra for hydrogen. And Bohr provided a way to explain this, the emission spectra. In other words, those lines represent the fact that the electrons in the hydrogen atoms are in certain orbits, the circular orbits for hydrogen, and that they were quantized. In other words, only those energy levels will be possible for an electron to jump up and to return down to its original spot to emit light. Only certain energies are resulting. So, as some might say, chemistry has been boring students for a long time. Well, the Bohr model perhaps, huh? All right. So another way of thinking about this line spectra, the yellow glow from the electric pickle is resulting from the applied voltage converting sodium ions back to sodium atoms, and when they're excited, they return to a ground state. Now we'll talk about ions later, but the ions from sodium are returning to a lower level, an energy level, and they emit light when they do. And that's what the yellow color is resulting to. Only those certain kinds of transitions from a higher energy to a lower energy are going to occur, and light emission occurs when those transitions occur. And if you wanted to get a cartoony value of it, here we have the atom with an electron who's supposedly out of place. Maybe this one is out of its element, haha. So let's think about how in the world we can think about or use these in calculations. And here's, we'll walk one through and get your calculator and write it down alongside the calculation as you please. When copper, metallic copper, is bombarded with high energy electrons, X-rays can be emitted. And if you're going to calculate the energy in joules associated with each photon, if the X-ray wavelength is this fraction of a nanometer, what on earth do we have to do? So we're looking for energy in joules, and it's going to be related somehow to wavelength. Well, we've seen a relationship that puts energy and wavelength together. So what would that be? It starts off with energy equals Planck's constant times the frequency. Wavelength is lambda. That's the other variable used in these things. And so lambda is related to frequency in this fashion. Nu is c over lambda. And so we'll have to use that with Planck's constant to come up with the energy. So energy is going to be Planck's constant times the speed of light divided by the wavelength. And Planck's constant is a number. You just have to get used to it or find it someplace. 6.626, 6.63 is close enough. times 10 to the minus 34th joules seconds. Watch the units here. Times the speed of light, which is 3 times 10 to the 8th. And divide that by the wavelength, which is 0.154 nanometers. Instead of the prefix n, you can put 10 to the minus 9. Nano means 10 to the minus 9. So it simplifies your conversions by just putting it in that way. If you pay attention to all the parts and the units, the seconds are going to cancel. One's on the top, one's on the bottom. The meters are going to cancel. One's on the top, one's on the bottom. And your exponents should make sense when you put it all together and put it in your calculator. The energy value then turns out to a value of 10 to the minus 15th joules. Could you have guessed this? Surely not likely. These are odd values to speculate unless you've got a lot of experience with them. But simply, it's an example of how we can put equations together or put the values together in these relationships with energy, Planck's constant, and the speed of light and wavelength. Comes up with an energy of a single photon from those X-rays. All right, a couple more thoughts here. The properties of matter are found to be described as having wave-like properties. A Frenchman, and I'll not say his name well because I don't speak French, but Louis de Broglie figured out that if light can behave in some respects like matter, then perhaps matter can behave in some respects like light. This was in the 1920s. In other words, matter has wave-like and particle-like properties, such that the wavelength, lambda, is related to Planck's constant, and the object's mass and its velocity. The velocity then, so the de Broglie hypothesis allows the calculation of the wavelength of an electron or of any particle or object if you know the mass and the velocity, because h is, that value is Planck's constant. And de Broglie's hypothesis reflects the idea that matter can sometimes behave like light in having wave-like properties with wavelength. So we'll not dwell on that, but in many respects, folks will tell you that electrons made us do it. Electrons are all where it all comes down to, how we make sense of everything. I will pause this